Medium carbon steels are a little different. So we have enough carbon, so now we're starting to get some hardenability. We can quench, we can temper, we can form martensite in these through some pretty traditional heat treatment ways. They typically have fairly low, but they can be heat treated with rapid quenching rates. So if we add more alloying elements, though, their hardenability can go up pretty significantly. That's with the higher alloy medium carbon steels. But these medium carbon steels tend to work in a little different way. These are still workhorse materials, but they're not used quite for those same structures. What you start to see are crankshafts and bolts, materials that need higher strengths, but still pretty good ductility in a lot of cases. If you think about hand tools, bushing, tubing, shafts, piston, gears, especially, you start to really see these types of turbo machinery type applications. And this is where medium carbon steels tend to come in. Now, high carbon steels, chisels, hammers, these are hard cutting instruments. They're the hardest, strongest, but they have really, in a lot of cases, not a lot of ductility. And so we use them in a hardened and tempered condition. They're wear resistant, which makes them very attractive for these types of cutting applications, especially since they can't hold an edge to them. So you start looking at the application for a lot of these 1080, 1095 steels, you start to see that. Now, the other area that they come into really play is in really the bearing and rotor type business as well. It's turbo machinery as well. But anything with a lot of wear resistance that you would be looking for, this is where high carbon steels come in. So what we see is a wide range of applications, and all we've done to the steel is changed the carbon content. Now, I like this figure for a number of reasons. It gives really a pretty good idea of where these materials sit with yield strength and where their applications are. So the structural steels and the low carbon steels are pretty much there, but as we start adding hardenable steels, we start alloying them, we start working our way up this yield strength way of looking at it. We're up to 100 KSI, so we're talking some pretty strong materials with 100 KSI yield strength. These are very high strength steels, but you can go into some steels for hardening. Some of these alloy steels, as you start adding more alloying elements, you start getting strength. But you can guess what happens is the tail end of that, typically your ductility goes down. Carburizing grades, these are gear steels for the most part. Anytime you want to carburize something, you tend to start with a low carbon content, but you can get some very high strengths after carburizing. And then there's this whole other grade of steels, these ultra high strength steels. Things like tail hook on Navy fighter jets. That tail hook material is made from an ultra high strength steel. It's a specialized steel. In a lot of cases, that Carpenter Technologies in Reading is really well known for their ability to develop and produce ultra high strength steels. And so we started looking at this from a strong steel that we might use for the hull of a ship up to something for a tail hook. There's a factor of 3 difference in yield strength. So you can talk about 300 KSI yield strength. That is an exceptionally strong material at the end of the day. So the hardness levels as well, different grades of steels. We work our way up the hardness. So we know there's especially in steels, that there's this connection between hardness and strength. And it's very well defined. It's fairly linear. But what we tend to see is we have these alloy steels, but the highest hardnesses that we get are what we consider carburizable grades. And if you go back to one of our earlier lessons in the course, we spent a lot of time talking about diffusion, and one of the major applications that we talked about with diffusion was in carburizing. And so that ability to produce a case on a steel structure, that high carbon area there, that's sort of where that carburizing comes in. And that's where high hardnesses come from. So at that point, we've sort of hit upon all of those major categories of steels with respect to low, medium, and high carbon steels. Now, as we move on, I think the next place to stop is to talk about tool steels. Now, tool steels are different. They are not really the way I look at it, and really the way you probably will see it as we move into a little more applications of steels. they don't fall strictly into a class of high carbon steels. I like to think of them as their own class of steels because they have a different strengthening mechanism. And I will reiterate that. Their strengthening mechanism is based on the formation of very hard and wear-resistant carbides because these steels have very specific applications. Look at some of them: drills, saws, lathes, tools. It's tool steels. They're used for machining tools for the most part. If you live in the Latrobe area, Kennametal is a major producer of these types of steels. The old Crucible steel was a major fabricator and producer of tool steels. These steels rely on the formation of wear-resistant carbides: chromium carbide, vanadium carbide, and WC means tungsten carbide. So the formation of these carbides is the primary strengthening mechanism for these tool steels. This is what gives them their properties of wear resistance. And so you tend to see some manganese properties change. Silicon tends to be high, but it's the addition of tungsten, vanadium, and molybdenum. These are strong carbide formers. These are the ones that really give them that ability to become tool steels versus just a high carbon or a plain carbon steel. So keep that in mind. Tool steels are strengthened by the formation of complex carbides. Now, sort of the steels, as we saw, is there's some different grades and how we can look at them, but steels are a little more numerical on how we can think about them. That 4-number grade tells us so much about composition and properties that we have that. Cast irons go back a little longer. I mean, historically, cast irons were used long before steel. Steels by the end of the 19th century were just a huge new invention at that point. Most everything prior to that had been built out of some type of cast iron. And so the cast irons, we tend to shift a little bit. In the steels, we really talk a lot about the iron-iron carbide phase diagrams. But if we shift to the iron-carbon phase diagram, we see some of our numbers for our eutectoid and whatnot shift a little bit. But really where we want to look for cast irons is cast irons are based off this eutectic. We had talked in the past about that ability to form a liquid to 2 solid phases at a single temperature and composition being important for an invariant transformation for casting. So we're going to take that eutectic and it's going to be the basis for cast irons. So how do they vary? Their carbon content is much, much higher than what we see for steels. We see that just from the phase diagram. It's based off this eutectic. It has a tendency to want to form graphite. There's so much carbon in it that it might go right past that iron carbide or that Fe3C right to the formation of pure carbon or graphite. Slower cooling rates might tend to favor this. That goes back to equilibrium type of issues. Silicon in this case will tend to promote that graphite formation. So if you have higher silicon contents, which you might add silicon for a number of reasons, fluidity of the liquid metal is one reason you might add a lot of silicon, you start to form graphite. And then these microstructures and mechanical behaviors will depend, as always, just with steels, on composition and heat treatment. Now, there are 5 major types of cast iron. Now, I will test you on this, and what I will primarily test you on are morphologies of them. So if we look at the gray cast iron is probably the oldest of the cast irons that we would typically use. It tends to be inexpensive. It's easily cast, which is where this high fluidity comes. So you can produce complex parts, has good resistance to wear, because if we look at this microstructure, it's got 2.5 to 4% weight percent carbon, which tells you right off that it's going to be very hard. The high levels of silicon promote these graphite formations. But in gray cast irons, we can have a pearlitic or a ferritic microstructure around it. They tend to be weak and brittle in tension, but they're much better in compression, which you would tend to expect for anything that's hard. They're very effective at damping vibrations. But let's look at what the microstructure looks like. The gray cast irons are primarily defined by these flakes of graphite. And so you can start thinking about in tension, why would they be weak and brittle? Well, you look at the ends of these flakes. They are very much stress risers. And so these stress risers will tend to limit that ductility and that strength in tension, because we already have a lot of high strain, high stress areas locally within the gray cast iron. Mechanical properties are good. You want to use them in castings. Cylinder blocks, heads, pistons, diesel engine liners are a big one. And it's that vibration, the damping of vibration, which will tell you for the most part that it has unique modulus characteristics. But the strengths, if we look at them, they're not all that good in tension. So you're going to want to use them in compression, and they're widely used. So remember this image for the exam. Ductile or nodular cast iron was, as we start moving from gray cast irons, which are a little older, we wanted to have something a little stronger. And so the idea was, let's take those nodules that we have, those flakes with all their stress risers, and get rid of them and convert them into something that doesn't produce a stress riser. This one, we get spherical particles. They tend to be rather large. We have a pearlitic microstructure around them with these graphite nodules. That's where the ductile or nodular cast iron. And so since it's named ductile cast iron, you would tend to think that it's much more ductile than gray cast iron. In a lot of cases, it approaches that of what we'd see for steels. And so this type of microstructure is going to require some type of heat treatment, usually a long-term heat treatment, about 700, very similar to a spheritization heat treatment. As we see, strength went up. Ductility is now in a measurable state. And so, you can have some valve and pump bodies, some high-strength components, pinions, gears. Still, you're looking at something with a high level of wear resistance, especially with this amount of carbon in them. But you look at them, it's significantly different. So ductile or nodular cast iron, you have nodules of graphite in it. So white cast iron, this would be your rapid cooling rates. It's extremely hard and unbrittle. It's virtually unmachinable. So is it used for anything? It's very limited in applications. If you would want to use it, it would have to be because you're going to really take advantage of its wear resistance. So this fast cooling rates basically traps a lot of the carbon into cementite. And so you have a lot of carbon. This is like one big carbide. And so low silicon in it will tend to limit the formation of those graphite nodules that we saw in ductile and gray cast iron. So it's a lot different. The other idea to get past is that you're not going to see a lot of white cast iron used in industry because it's intermediary, which makes it a little unique, is that you produce the white cast iron and then you heat treat it to give you malleable cast iron. Now, if you look at that microstructure, you're going to say that is something much better. So the graphite can come out, it forms clusters after a significant prolonged heat treatment where you can decompose that cementite and start forming graphite. Microstructure is fairly similar to nodular cast iron, except they're a little more flaky. They're not very much nodules. But if it's malleable, it has pretty good ductility, high strength, and so it's typically a higher temperature material. So this was sort of the progression of cast iron from gray to nodular to malleable with white in the middle. And then compacted graphite cast iron is sort of where we've come from. It's used for some other applications. And so its microstructure is still ferritic around these graphite worm-like vermicular shapes, we can call them. But they tend to be used for some other applications. High thermal conductivity, resistance to thermal shock. And thermal shock is a pretty big deal in cast irons because it can lead to some cracking and other issues. And then it has good oxidation resistance. So this is where we start to see in diesel engine blocks and exhaust manifolds and brake discs in high-speed trains, something where we need to really take advantage of that ability to conduct heat away. And so that's where the high thermal conductivity comes into play, and with some reasonable ductility for a cast iron, but not much. So I would say, as we work our way through this, is be able to identify the different microstructures for the different cast irons and have an idea of what we're using them for. We're using them primarily, not always for structural applications, but for some of the other characteristics they have. And that's where that thermal conductivity, that wear resistance, that resistance in some cases to thermal shock, places where we can take advantage of producing of a material that is probably not that easy to machine, but that we can cast into the shape. And that's really where cast irons tend to fall now. They were much more widely used 100, 150 years ago. Not so much today, but still in use, in fairly broad use for some very specific applications.